Hello again. We are moving on in our discussion of exponential functions. We're going to talk about exponential growth and decay and what those functions look like, how to solve for particular values, and so on. So this is lesson 11.2, so let's get started. We're going to look at the base. Okay, the base is going to determine whether we have exponential growth or exponential decay. That's how you can tell which one you have. So every exponential function can be written as some constant a times a base b to an exponent x. And remember, x is the variable, a and b will both be constants. Now if b, that base, is greater than 1, then we have exponential growth. If instead it is between 0 and 1, then we have decay. If it was equal to 1, then all we would have is a bunch of y values that were equal to each other. And if it was 0, the same thing would happen. And we really don't talk about what happens if the base is negative, because that's kind of there's not a lot of situations where you would want to model that type of situation. So we're just going to stick with those two situations. And once we figure out the base, then we can talk about how to graph it and what numbers to plug into the equation. So if something is growing at a certain rate, then we add that rate as a decimal to the number 1. So for example, if I know the population is growing by 23%, then my base is actually 1.23. So that's 100% of what it was, plus 23% of what it was. So it's actually 123% of what it was before. If something's decaying, then I subtract that amount from 1. It is decreasing. So if a factory output is decreasing by 19%, then I subtract the 0.19 from 1, and I get a base of 0.81. And that's between 0 and 1, so that means I do, in fact, have exponential decay instead of growth. So here's an example. I've got some frogs. The population of those frogs is 400 when I start, and it's growing at a rate of 8% per year. So how many will there be in 20 years? Okay, so I think about what my starting value is. That's what A represents, how much I start with at the beginning of the time that I'm talking about, and that's 400. Now since it's growing by 8%, I take that 0.08 and I add it to 1, and that's where the 1.08 comes from. And x is my exponent. So if I want to know how many there will be in 20 years, I just let x equal 20. Y is going to equal 400 times 1.8 to the 20, and that's going to be about 1,864 frogs after 20 years. All right, now let's talk about a second example. Obviously this one will be about decay. So I have a 90 kilogram substance that's buried and it's decaying at a rate of 1.4% per year. Okay, so how much will there be in 18 years? Well, what I do is I take that 1.4%, which is 0.014 as a decimal, and I subtract that from 1, and I get 0.986. That's where that base comes from. My starting value is the 90. That's what it was. That's how much it weighed when it started. So that's my A. So my equation is y equals 90 times 0.986 to the x. And if I want to know how much will be left after 18 years, I simply replace x with 18, and the rest is already in there, so it just becomes a matter of evaluating that, and then that becomes 69.8 kilograms. So that's how much is going to be there after 18 years. So that's kind of a brief introduction into exponential growth and decay. If you have any questions, please let me know, and I will see you tomorrow.